Howdy and welcome back to EET 260 microcontroller applications. And I just wanted to do a quick video talking about pulse width modulation and how it works and that sort of thing. And you may have seen this kind of a thing before, but just either for review or for getting it for the first time. Pulse width modulation is a technique that's used certainly in electronics, but also maybe in other areas too, where one, instead of trying to drive out an analog value, to drive out a certain current or a certain voltage, an analog kind of means that voltage would be continuous in time, and it could be any value on a continuum from one value to another. And so in our case, we're going to talk about 0 to 5 volts. And we're going to try to show the difference between a pulsed value and its equivalent in an analog value. The idea here is that there is some kind of conversion that goes on from the quick changing pulsed values here, the values that are either at 5 volts or 0 volts, and that's it, to some average value that occurs here. And for something slow like the magnetism in a motor, or if you look at especially an incandescent light bulb where it has to heat up to glow and produce light, or even an LED where our eyes are kind of slow to recognize that it's being turned on and turned off. This technique of pulse width modulation is a way that one can use a digital driving system to produce an equivalent analog output. So you can think of it as a kind of a digital to analog converter, or D to A converter, as some people will say, or a DAC, D-A-C. So in this case, what we're going to do is we're going to take some switch of some kind, and we're going to connect 5 volts to a load. In this case, we're going to do it for 1/5 of the time. This idea of duty cycle is the period of this waveform. And if you look here, it starts at 0 and it goes to about 1,000 microseconds, and that's the same as 1 millisecond. So this is a thousandth of a second is the period, that amount of time. And if the period is a thousandth of a second, then you can have 1,000 of these cycles in 1 second. So the frequency of this waveform is 1,000 cycles per second, or 1 kilohertz. Kilo meaning 1,000, hertz is the unit name for a cycle per second. So once again, we have 1,000 microseconds. That's 1 millisecond, 1,000th of a second. So in 1 second, you can have 1,000 of them. And so the frequency of this repeating pulse here is 1 kilohertz. Now, if we drive this into something slow, like a DC motor, what will happen is the motor will just kind of laugh at this pulsing thing and say, I'm just sort of going to integrate, if you will, or kind of take the average feel of these punches, and they feel like I'm being hit with something that's about 1/5 the full voltage, because it's the full voltage on for 1/5 of the time. And what I did over here is I took an Excel spreadsheet, and you can reproduce. I'll post this spreadsheet, this workbook. It has 3 spreadsheets in it. I'll post it. I think you could probably open it in Google Docs if you wanted to. But I have microseconds written down here, and I have volts, and then I have this averager. So every 50 microseconds, I update the value here. And I have made the duty cycle 20%, which, and I think I've got a fancy formula here which will actually be equal to 5 for the first fifth of any cycle, and then it'll be equal to 0 volts for the rest of the cycle, and then 5 for the first fifth, and 0 for the next 4/5. And you can see that graphed out here. We have this waveform, and I think you can believe that this is 1/5 of the time from here to here. And the period is the time between any two like points on the periodic waveform. So this corner here and that corner there are like points, and so this is high for 1/5 of the time and low for 4/5 of the time. And you'll notice I gave our graph a well, the way Excel graphed it, it made this a non-zero rise time. So this is kind of what you'd see more like in real life here. You'd see a slanting edge. You obviously in real life cannot change an output from 0 to 5 volts in no time. It takes some time to change things. There are capacitances and inductances and all sorts of real world things out there that limit your ability to switch from say 0 volts to plus 5 voltage, or really to switch between any two quantities in 0 time. Everything in the world takes time. So here we go. Here's our waveform that's high for 1/5 of the time, and this green waveform here is the averager. The averager starts out a little later, and I don't know if you can see it, but the averager basically takes the last 20 of these, because there's 20 of these in one cycle. That's the secret. So it takes a cycle and it averages the voltage in a cycle. And at the end of one cycle, it says, oh, you've got about 1/5 of 5 volts or 1 volt. And you see that out there. Just to speak to this in the signal processing domain, this waveform here, this pulse waveform, has some rapid changes in it. Those represent what we'd call high frequency energy. In other words, if you could just analyze that one slope right there, you'd say to yourself, this has some rapidly changing voltage here, and that represents a high frequency. Because, at a high frequency, take a high frequency sine wave, it goes up to its max and down to its min many times per second. So it changes quickly. So quick changes are associated with high frequency content. Well, an averager is a great low pass filter. And so what this low pass filter is doing is this averager is a low pass filter. It's allowing low frequencies through and not allowing the quick changes or the high frequencies through. So this low pass filter here, this averager, is saying all I feel when I sum up an entire cycle and divide by the number of samples in the cycle, all I feel is 1 volt. And a motor for whom you are applying this kind of waveform would say the same thing, says I feel the oomph of about 1 volt DC. And so that's pulse width modulation. We can oftentimes create an analog effect by trading time for the ability to control voltage on a continuous basis. The other thing that's neat about pulse width modulation, and another reason why it's so prevalent, is because if I implement this with a switching device, let's say we have a motor, and I have one transistor, and the transistor is either on or off. When the transistor is off, there's no current flowing through the transistor, so the transistor can't be dissipating any power. Because power is voltage times current. If the current is 0, the power in the transistor is 0. And I don't need a heat sink for a transistor that's dissipating 0 power. Now, during the times the transistor is on, and I have some current going through the transistor. Now, if I take that current and I square it and I multiply it times the effective resistance in the transistor, I have the power that's being dissipated in the transistor. If I were to take a copper switch and turn it on for 1/5 of the time and then turn it off for 4/5 of the time, that copper switch, being such a good conductor and having such low resistance, wouldn't dissipate much power when it's on, and it'll certainly dissipate no power when it's off. So the better that we can approach a high quality copper contact switch in our switching device, which turns the power to the load on and off. Let's say I have a transistor here like these modern MOSFET transistors that get down in the thousandth of an ohm. Well, you can imagine you can put a lot of current into through a transistor whose resistance, let's say it's 8,000th of an ohm, because those are not hard to get transistors that can do that. Well, if I had 8,000th of an ohm, let's say I put 5 amps through that. Well, I square my, it's I squared R. I square my 5 amps, that's 25 amps squared, and then I multiply it by 8 thousandths of an ohm. Well, I'm going to be down in the 25 divided by 1,000 is 0.04. You multiply that times 8 and you get 0.32. So for 1/5 of the time, that transistor would dissipate 0.32 watts, and so its effective power over the whole cycle would be 1/5 of that, would be about 0.064 watts. And I'm gonna double check myself here because I'm not drawing any diagrams or anything, and I'm talking off the top of my head. But if I take 5 and I square it and I multiply it times 8,000ths of an ohm, well, I did that wrong. I actually came out with 200 milliwatts. So, sorry about that. 200 milliwatts, 0.2 watts while it's conducting. And 1/5 of that would be 40 milliwatts. You can imagine a device like that. You could put 5 amps through it and drive a pretty powerful motor with 5 amps, and the device wouldn't even need a heatsink. So that's another reason. In fact, some audio amplifiers now, instead of trying to drive a continuous sinusoidal value between a minimum and maximum, they put out a series of pulses of various widths, so that this average voltage will track what the sinusoidal waveform would have been, or whatever music waveform you have. And if you can do this fast enough and use good quality MOSFETs, you can make what they call a Class D audio amplifier and produce pretty decent music. I'm sure there are audiophiles who would argue how good it is and that sort of thing, but many subwoofer type drivers, which tend to run at low frequency anyway, use this technique, and you see them in cars and they'll say, well, this is a 1600 watt amplifier, an 800 watt amplifier, and it's a kind of a clamshell type thing of cast aluminum. And if you open it up, there's a little bit of electronics in it and a bunch of MOSFET transistors bolted to that case. And so that's how they achieve their claimed power delivery through these things. Now, how much power in terms of classic watts do they really deliver? They have all these terms like peak power and that sort of thing. Yeah, that's a discussion for another day. But when moving motors around now, you can turn a motor on and off with something that may or may not require a heat sink. The ones you use in class, the H-bridge drivers, we'll talk about H-bridge drivers, the L293, may require a heat sink for some motors because it uses bipolar junction transistors, and they can't achieve quite the conductivity or conductance that a MOSFET can. So they may require a heat sink. But even those are compact, and they represented quite a step forward in terms of being able to control motors. And this technique, it's even used in super precision brushed DC motors in CNC applications, where pulse width modulation is part of the driving driving method. And there's a lot of things that go on mathematically to make it behave so that they have a proper control loop, and that it behaves exactly as they like to get the best precision, and that sort of thing. But again, average out a bunch of pulses and you can get what looks like an analog voltage, and that's what pulse width modulation is all about. If I go to the second page, all I'm doing here, I changed this number to 40%, and that affects how long this is 5. So now our 5 volts goes for about 2/5 of our cycle. The cycle is still, you see the 1,000 down here? The cycle is still 1 millisecond, but now the switch is on for 2 parts of that. So if I use that MOSFET I was talking about, I'd be up to a whopping 80 milliwatts of power dissipation now, still no problem whatsoever. And the average of this thing, instead of being 1 volt now, is 2 volts, because that's 40% of 5 volts. And all we have to do is operate this duty cycle in the way we want, to the precision we want, and we're basically producing an analog voltage, or an analog effect out here for driving the motor from a digital system. The system can only go between 0 and 5 volts, but we get to play with time, and that's where we trade kind of something approaching analog time. Obviously we can't get complete continuous time. There's some number of samples. We count something here to time this, but we can get a pretty smooth, almost seemingly continuous range of voltages here by just playing with the time that we drive this high. I think we've said that enough times now. And here's 80% duty cycle. So it's high 4/5 at a time and low 1/5 at a time. And this kind of looks like, and there's the average at 4 volts. If you think about it, this kind of looks, well, not kind of, it really is this waveform turned upside down. Okay. And is that meaningful at all? No, I don't know. I just thought it was cool. But here we are up at 4 volts, which is 80% of 5 volts. That's our average voltage, and you can see we're turning it on for 4/5 at a time. So now we're at a walloping 160 milliwatts. That's about 1/6 of a watt. And there's a lot of small integrated circuit packages that can easily handle that. And again, this is for a 5 amp load to a motor. So that's really what I wanted to say about pulse width modulation and duty cycle. Duty cycle is pretty easy. It's just the percentage of on time divided by the total time, the period of the repeating waveform. So I got 1 millisecond, and I'm on for about 0.8 milliseconds. I mean, that's an 80% duty cycle. So you can control your motor, and you'll see this happening in our other videos. So that being said, we'll get on with other kinds of motor control, but sometimes under the hood, as we'll mention, sometimes under the hood of these other motors, be they positional servo motors, continuous rotation servo motors, or brushed and brushless DC motors and all that sort of thing. This technique is most often the one used to control the brightness of some lighting, or the speed of a motor. It's also used in switching power supplies, which makes sense. You got this switching thing, and with some inductance and capacitance, you can make a low pass filter. And with 5 volts in, you could produce, say, 3.3 volts out, or 2.5 volts out, or 1.8 volt out. And so the switching technique, pulse width modulation, is at the heart of a lot of power supply designs. And as long as you use good quality components, you don't waste the power. You truly transform the power from one configuration, the voltage and current, from one configuration to another configuration that's regulated where you want it. And those systems, like some of the motor control systems, those systems have feedback to say, I want 3.3 volts. You're now a whisker high. Maybe you should make your pulse width a little bit, shorter. Or I'm at 3.3 volts and I'm just a little bit low. Please make your pulse width a little higher. And so with a feedback control, you can actually transform the power to a regulated, say 3.3 volt, or whatever your desired output voltage is. You can transform it to a regulated voltage, and you're not wasting the power. The low pass filtering, again, with good components, is helping you reconfigure voltage and current shapes so that the power delivered to a load has been usually transformed in time by storing energy in inductors and capacitors, and releasing it back so that the output looks like what you want. And again, those are going to be low pass filter structures, because you want the output you want is at DC, which is often considered to be 0 cycles per second, or 0 hertz. There are no cycles present in a constant DC level, so it's often referred to as 0 hertz. And so you need a low pass filter to knock out any high frequency stuff. And what that low pass filter will do, if it's efficient, is it doesn't reject the energy. It stores and releases the energy in a way that results in this very close to flatline DC value. Okay, I think I've yacked enough on that. Please email me if I'm doing too much yakking without diagrams and things to back it up. I want to be careful not to go off and recapitulate a ton of electronics education while we're studying microcontrollers, but these concepts we're talking about now with motors and pulse width modulation and that sort of thing are they're just used all over the place. And so from robotics to like you will hear me say, automotive, the motors that drive things in cars, to any vehicle type thing where could be an airplane, could be a train, it could be a ship, wherever you're doing this servo mechanism thing, could be audio circuits, as we said earlier. There's so many places where this technique is used. All right, take it easy, and we'll keep on going with motors, and hopefully we'll support you well for the labs that you're doing this week. Take it easy, and we'll be in touch. Bye.